Hi, my name is Said Mahmood, and today I'm presenting my paper, which is Learning Semantic Relationships of Geographical Areas based on Trajectories. And I wrote this paper with my supervisor, Professor Manos Papagelis. So before we go into the details of the paper, let's cover up some of the basics. So in the slide, we can see an observation space, and it has a bunch of red lines going inside it, and we call those lines as trajectories. So trajectory is basically a spatio-temporal information of moving objects, and each trajectory can be denoted by the geolocations, which are x, y, t, and these are the latitude, longitude, and the timestamp. So moving further, because our research is in the area of trajectory data mining, so the purpose of trajectory data mining is to discover patterns in trajectories to inform critical real-world applications. In terms of the trajectory data mining tasks, you can use them for trajectory similarity. You can cluster trajectories based on their similar movement paths. You can use them for anomaly detection. You can classify them, and then definitely you can predict new trajectories based on the previous trajectories of a person, and so on and so forth. So moving further in terms of the trajectory applications, we can use them for human mobility understanding. We can also use them for healthcare, in which we can detect the changes in the gait pattern of seniors. And there's an interesting use case, which is the education-based services, that you can recommend point of interest to people based on their previous interaction with the point of interest. So in terms of the research questions that we try to work on in this research, before I go into them, I would like to cover up one of the very basic concept that we use again and again in my presentation. So it's called geographical proximity and semantic proximity. So in the figure, you can see that this is I call as observational space, and these two green rectangles, we call them as grid cells, or you can say geographical area. So we say that if the geographical areas are physically close by, we say them they have geographical proximity. And then if they are physically far apart, but they have a lot of trajectories passing through both of them, then we say that they have semantic proximity. And semantic proximity, what I mean by that, it's explained in this slide, that you have this observational space, and then you have these two green rectangles over here. These are the grid cells. So in this case, the blue lines denote the trajectories that are passing through both of the grid cells, both of the geographical areas, and the red lines denote the trajectories that are passing through either of them. So based on that, we say that if a lot of trajectories are passing through two different grid cells, even though they could be physically far apart, then it means that they share semantic proximity. By semantics, we mean that in terms of their meaning, in terms of the understanding of people living in that area, they have a meaning in terms of the movement paths of people. So moving towards our first research question is that how people perceive different areas of their city. So again, we have three rectangles inside our observational space, and we would like to know that how people living in the city perceive these areas. Or eventually we're going to divide all of the observation space into grid cells, and we would like to understand how people perceive different areas of their city. Moving to our research question 2 is that to what extent people rely on geographical proximity of area. What we mean by that either people travel to locations which are physically close by, which have geographical proximity, or either they move to places which have semantic proximity. It means that they share a meaning. For example, a person traveling from his school, from his house to university, and etc. So going to our research question 3 is that how the behavior of people compare in different geographical space. So in our research, we worked on the data set coming from two different cities. The city 1 is the New York City, and the city 2 is the city of Porto. Moving to our two methods. So our first method, we try to learn the semantic relationships of geographical areas, and in the second method, we come up with statistical methods to distinguish geographical proximity from semantic proximity. So let's jump into our first method. So in this method, we look at the observational space, and then we take the example of one single trajectory passing through this observation space, and then we divide the space into grid cells, and again we look at the trajectory passing through those grid cells. So Now the question is that why do we need to divide the observation space into uniform grid, into grid cells in the first place? So the reason is that if you do a direct analysis in terms of comparing or in terms of relating trajectory with the observational space, it's very computationally expensive. So to avoid that, we divide the area into grid cells. And this is explained in this slide much well, is that a trajectory is a set of geolocations XYT. So we look at the trajectory passing through the grid cells, and then we abstract the trajectory from geolocations in the form of grid cells. And this abstraction reduces the computational cost, and it makes it easier for you to understand the geographical areas. So to have a reminder that each of this rectangle represents a geographical area inside the observational space. Moving further, once we have all of this method that we move from observational space to having trajectories on top of them and dividing them into the grid cells, now how can we find relationships between those geographical areas? So for that, we use the approach of network representation learning, and then we use a random walk based NRL. So according to that method, you have an input graph, and then you take random walks on top of the input graph, and then moving further, you treat those random walks as sentences, and then you feed those sentences to the skip-gram neural network model. And then from that, you are able to obtain the vector embeddings of each of the nodes inside the input graph. So what NRL does, the random walks NRL does, it tries to preserve the structure of each of the, it tries to preserve the structure of the input graph, even though it reduces the dimensions. So this input graph could have maybe 1000 dimensions, and then after doing all of this process, we are able to obtain the vector embeddings of each of these nodes, but these vector nodes are in 128 dimensional space, which are easier to work with. So moving further, how we use this NRL in our work, so we have the observational space and we divide that into grid cells, and from that we construct a lattice graph by creating edges between each of the adjacent grid cells. We are able to obtain a lattice graph, and then we take trajectories as walks on top of the lattice graph, and from that we generate walks as grid cells. Moving further, because there is one thing that we try to tweak inside the skip-gram model. So according to the skip-gram model, the nodes, it's based on the idea of context window. So what I mean by that, it could be looking at the first three nodes, and then the next three nodes, and so on and so forth. So in skipgram, the nodes that are appearing in the same context window are more similar. But in case of the trajectories in our work, every node should be in the context of every other node. So what I mean by that let's say that you have one single walk of trajectory. So what we want, that even though this node and the first node are not coming in the same context window in case of the skipgram model, but we want then, regardless of the context, if all of the grid cells are part of one single walk, they should have the exact same amount of similarity. So to be able to solve this problem, what we do is that we shuffle one single walk m different times, and we feed those m walks to the skipgram neural network model. So what this shuffling does is that it neutralizes the effect of context nodes, and distant nodes will not be less weighted than the nearby nodes. So now we go to our second method. So in this method, we discuss three different models, and then we also have a null model, which is based on the null hypothesis that people perceive as a city based on geographical proximity. And geographical proximity is the physical closeness between different areas. And in this second method, we try to disprove that no, people don't move based on the geographical proximity. Rather, they move based on the semantics. They move based on the semantic proximity. So let's talk about our first model, which is the real model. So this model is based on real trajectory movements over the lattice graph. So we give those trajectories and the observational space, which we divide into grid cells, to our first method, and then we obtain the vector embeddings. Moving further, we have our null model, in which is based on the random walks. So But what we do in this model is that we have one constraint that we say that, okay, the size of the random walk should be equal to the average of the size of the real walks based on the real trajectories. And then we give this to our first method, and then we obtain the vector embeddings. Moving further, we have an alternate null model, which is intermediate model. So in this model, we try to satisfy one more constraint, that the starting node of each random walk is exactly the same as the starting node of the walk coming from the real model. So those walks were based on the real trajectories. And the main motivation for this model is to learn vectors that can capture more of the constraints of the real trajectories, but still maintain the unbiased random walks on the lattice graph that are still dictated by geographical proximity. So moving further, once we have all of the three models, we would like to compare them. And for that, we have two metrics. The one is quantitative metrics and the other one is a visual metrics. So let's talk about our quantitative comparison. So the first one is the cosine similarity. So given three vectors which have 128 dimensions, what we do is that we obtain cosine similarity between the vectors. So what we say that we are able to come up with a threshold value, which is lambda a. So we say that if the cosine similarity between two vectors is greater than equals to lambda a, then we say that these two vectors are similar. And in the other case, if the cosine similarity is less than lambda a, then we say that these two vectors are not similar. In terms of another quantitative analysis, we try to find interesting pair of nodes. And what we mean by that, let's say that you have two models. So the model X could be the real model, and the Y could be the null model. So we obtain all the cosine similarities between different vector nodes in each of the models, and then we take the difference of the cosine similarities from two different models. So what this difference gives us, it's we are able to come up with the threshold value lambda v, and we say that if the difference is greater than equals to lambda v, then the two nodes are interesting. And in the figure, you can see that these two nodes, they are physically far apart. So if you're looking at the null model, their cosine similarity could be very low. But in terms of the real model, their cosine similarity could be much higher, because a lot of trajectories could be passing through both of these grid cells. So in nutshell, the difference between the cosine similarity from two different models gives us the most interesting pair of nodes, because they depict the very high amount of cosine similarity between the nodes from two different models. So moving further, we also compare the distribution of models using histogram. So in the figures, you can see that on the x-axis, we have cosine similarity, and on the y-axis, we have the total number of pair of nodes. And then we compare the distance between two histograms coming from different models. And then for that, we have the chi-square. So in terms of our exploratory analysis, we obtain the many-to-many visualization from all of the three different models, which can provide summary of how embedded vectors are organized in the low-dimensional space. So now I go back to our last research question, that how the behavior of people compare in different geographical space. So as mentioned before, we worked on data sets coming from New York and city of Porto. So to be able to answer this question, that how people behave in living in different geographical, in different cities, in different geographical space, we go back to chi-square, which is the distance between the histograms. So according to chi-square, the closer to 0 the result is, the higher is the similarity between the histograms. So what we see that our result is way much higher than 0, which says that the real model is quite different than the null model, because real model is based on the semantics between the areas, and the null model is based on the geographical proximity. And these values helps us in understanding how two different cities, like city of New York or city of Porto, or it could be any other city with trajectories, and we could say that how much they are different from each other in terms of the movement paths of people. So in terms of the summary, we went from all the way to trajectories and in the observational space, and we divided the observation space into grid cells, and then further we generated a lattice graph from the grid cells, and then we took trajectories as walks on top of the lattice graph, and then we obtained vector embeddings for three different models, and then we gave those vector embeddings to our statistical method, in which we try to distinguish between geographical proximity and semantic proximity. Thank you very much.